Okay, here in Lesson 6, we're going to build off of some of the things we've learned in the previous videos. We're going to talk about and or. We're going to use them together in some cases. We're going to involve finding probabilities directly with tree diagrams. And we're going to also explore the idea of conditional probability a little bit better now that we have the and or formulas. And finally, we'll finish by talking about something called Bayes formula problems, or a priori or a posteriori probabilities. To review, here are a summary of the and or rules, and this is actually how I remember them. I remember them by picturing a diagram. So when somebody asks me to analyze something related to an or situation, I always picture a Venn diagram like this, right? I have two events that are overlapping in general, A and B, and then I remember that the probability of A or B is the probability of A plus the probability of B, but I have to subtract the overlap A and B. Right, so I do have to remember that or is addition, but then I have to remember to subtract the overlap. And there's a special case for that, disjoint events, where the probability of A and B, the overlap is 0, then the formula simplifies to just A plus B without the overlap because the overlap is 0. When we're talking about and, I remember that and is multiply, but to be able to reconstruct the formula correctly, I think of the top portion of a tree. So if I'm talking about events A and B, I put A and then B in the form of a tree. This is the probability of A. This is the probability of B given A occurred. That has to be a conditional probability. And then the probability of A and B would then be the multiplication of those two probabilities. So the probability of A and B is the probability of A times the probability of B given that A happened. And there's a special case here as well. It's called independent events, when the probability of B given A is just the same as the probability of B because it's not changing depending on A. So the and formula simplifies to the probability of A and B is just probability of A times probability of B. You can solve a great many probability problems just by understanding the use of these formulas right here and their special cases. So they're very important to understand and be able to recreate. Okay, and we often need to use them together to solve problems. So let's consider this example here. 5% of the people in a city have a certain type of cancer. There is a test to detect this cancer. If a person has this cancer, the test is positive, detects the cancer 90% of the time. If a person does not have this cancer, then the test is positive, in other words, gives us a false positive 15% of the time. If we give a person from this city the test, what's the probability that the test will be positive for the cancer? So because the test definitely depends on the cancer, it makes sense for us to analyze this by using a tree diagram. So let's go ahead and represent this with a tree diagram. We'll say basically the test is going to occur after the person has or doesn't have cancer. So we'll put cancer as the first event. A person either has cancer or they don't have cancer. Remember, the line over something indicates the opposite of. So this means not having cancer. Right? And then we could have the test could be positive or the test could be negative for cancer. The test could be positive or the test could be negative, whether we have cancer or we don't have cancer. Okay, so let's try to read through the problem again, but this time we're going to put on the tree diagram the percentages that we can from the wording. It says 5% of the people have this type of cancer. That's why this probability here is 5%. That's the probability of all the people having cancer. It says if a person has the cancer, the test is positive. So that's the conditional probability. Given that someone has the cancer, there's a 90% chance of having a positive test. And that's why that 90% is put right there on that branch. It's a conditional probability. If a person does not have cancer, so that we're here in the tree, the test is positive 15% of the time. That's why this branch here is 15%. That's the conditional probability of having a positive test given that we don't have cancer. Okay, so those are the three numbers in the problem, and that's where they would fit on the tree diagram. We can use the fact that at every level, the probabilities have to sum to 100%. So we know that at this level, right, where the simple probabilities, they have to add up to 100%. So if there's a 5% chance of having cancer, then there must be a 95% chance that people don't have cancer in this region, right? Once we are into the condition of having cancer, this is a complete set of choices. So that also has to sum to 100%. And that means if there's a 90% chance of having a positive test, there's a 10% chance of having a negative test result. Same thing down here. These have to sum to 100% as well. So if there's a 15% chance of having a positive test, there would have to be an 85% chance of having a negative test. So we can fill in the rest of the probabilities in the tree. And then what we're trying to find here is what is the probability the test will be positive for cancer? we need to find the probability the test is positive, but that's actually in two places in the tree. I've marked them here with arrows. We can have a positive test because we have cancer and have a positive test, or because we don't have cancer and have a false positive test. Okay, so I'm going to have to somehow combine these right here and figure out the total probability of the test being positive. So you can think of this as two paths through the tree. On each path, one thing and another thing has to happen. So for example, on this top path, the person has to have cancer, and they have to have a positive test. Right? On the bottom path, they have to not have cancer and have a positive test. So to get the probabilities at the end here, we would use AND case rules. And AND says we multiply, but the second probability is conditional. So the probability of having cancer and having a positive test would be 5% times 90%, and that turns out to be 0.05 times 0.90. Okay, we'll leave it in that form. The other way to have a positive test is if we don't have cancer, 95% probability, times the probability of having a positive test given that we don't have cancer, 15%. So 95%, 0.15. So we can fill out those end node or leaf probabilities for the two probabilities of ways to get positive test. But we still have to combine that, because that means we can have a test that's positive from this, or we can have a test from this. And when we have two things that are combined with an OR, that means we have to add the two probabilities, right? So these are two mutually exclusive possibilities, and so that means the overall probability of having a positive test would be the chance of getting a positive test the first path, plus the chance of getting a positive test from the second path, which turns out to be 18.75%. So if I randomly test a person from this city, there's an 18.75% chance that they will have a positive test result. And we had to combine both the AND formula to find the probability through one of the paths with the OR formula and add, so to get the probability of combining two different pathways to get that, right? So AND and OR rules are frequently used together in this way to find probabilities. Okay. We use AND for each path probability, and we use OR to combine the multiple paths. So now that we've looked at that, I want to take a closer look at conditional probability. In a previous lesson, I think it was lesson 3, we defined conditional probability. And now that we have the AND formula, we can explore that a little further and give a formula for conditional probability. So to find the probability of B given A, we can represent the situation with a Venn diagram, right? We know the probability of B given A, right? The given A part has to relate to the bottom of the fraction, probability or count of the conditional sample space. That's going to be defined by A, and the top of the fraction we know is defined by the probability of what we're finding, the desired probability or count within the conditional sample space. So let's try to build that and see what that relates to in terms of the Venn diagram. So the condition here is A. That would be the probability or count in the conditional sample space. So that means the area inside the A circle. Okay. The top, the numerator, would be the part inside A that meets the condition of the probability we're finding, which is B, the part of the event that is in the conditional sample space. So it would be the part of the conditional sample space A that is the desired case, which is event B. So the part of B that's inside of A. So it'd be that shaded region there. Okay, so the probability of being in the A circle, the blue here, is just the simple probability A. It's the probability of A occurring, and so that would be best represented by probability of A. The probability in the numerator is the overlap, which we now know is the probability of A and B. So I'm going to use that symbol for this red part, the probability of A and B. And that means the probability of B given A is the probability of A and B divided by the probability of A. Okay, this gives us what most books call the conditional probability formula. I think it's hard to understand what conditional probability formula is what conditional probability is from the formula, which is why there's a lesson 3 video on that without using the formula at all. But now that we have the ideas, we can build the formula from our conceptual understanding of conditional probability. The probability of B given A is the probability of the overlap of A and B divided by the total probability in the circle A. That's really the meaning of that formula. Okay, but notice this is really just the AND formula, except solved algebraically, right? If I start with the AND formula, the probability of A and B, and we know that that's equal to the probability of A times the probability of B given A, which I think is much easier to remember because we can picture a part of a tree. Then if we just divided both sides by probability of A here, then we would get the probability of B given A is the probability of A and B divided by the probability of A, which is the conditional probability formula. So if you ever have a need to be able to write out the conditional probability formula, I just remember the AND formula, and I can always produce the conditional probability formula by just dividing by the probability of A. Okay? All right, so let's find a conditional probability for the cancer test situation. Here's that tree again with the probabilities filled in. And let's say, what is the conditional probability that if a person has cancer, they will test positive? So that means the if a person has cancer is the condition. So that's going to be the condition, and we're finding the probability that they will test positive. So the probability of testing positive given cancer. Okay. So using the conditional probability formula, if we wanted to do it that way with the formula, we should be able to enter the numerator and denominator probabilities. The probability of testing positive given cancer would be the probability of testing positive and cancer divided by the probability of cancer. Okay, so the probability of cancer by itself is 5%. It's this one that I have circled here. That would be the denominator of the fraction. And then the numerator is the end node and probability of testing positive and having cancer, which would be 0.9 times 0.05. So it would be 0.9 times 0.05 divided by 0.05. The 0.05s are going to cancel and leave me with that the probability of testing positive given cancer is 90%. But what I want you to notice is that 90% is a probability on our tree. It's the probability on this branch of the tree. Now, why is that way? It makes sense because, remember, conceptually we said that conditional probability means we define a conditional sample space, and that's the probability of something happening within the conditional sample space. So another way to think of this is, if the condition is cancer, then we can consider what part of the tree is related to cancer. Well, that's this square that I have marked out here, this rectangle. Only this part of the tree relates to having cancer. Everything else in the tree is something that's not specifically related to cancer. So if cancer has occurred, you're in this part of the tree. And then I'm just asking, what's the probability of testing positive in that space? Well, that's just this one branch right here, and that's why that probability is 90%. So it's a portion of the tree and then a probability within that portion. Okay, so there we go. The test part is 90%. So this is a really good way to use a diagram to find conditional probability. Find the area that represents the condition, and then within that area find the probability of the event. We can do this in a tree just like we do in a Venn diagram. It just will be a portion of the tree. Okay, now we're going to use that idea of figuring out a portion of a tree and then finding a probability inside that to find a conditional probability but going backwards through the tree. So let's find a different conditional probability. We're going to find the probability that if a person has a positive test result, they really have cancer. Okay, so we're going to use our idea of dividing the tree up by the condition. So the conditional sample space will be defined by this. Where is the test positive? So the test positive means that there's a portion of the tree, but it's actually kind of spread out in different paths. So really these two entire paths here represent the conditional sample space of the test being positive. So if I want to say, okay, the denominator here is going to be whatever the probability is of being in that conditional space. So that would be the probability of being at this end node here is 0.05 times 0.9, and the probability of being in this end node here is 0.95 times 0.15. And since I can be there this way or this way, that means I would add those two. So the probability of the conditional sample space is all the ways, the total probability of being testing positive, which is 0.05 times 0.90 plus 0.95 times 0.15. So we either need to represent the conditional sample space with some sort of a count or with some sort of a probability. And then as long as we use probabilities and stick with probabilities, we're fine. So this blue over here is the calculation for the probability of being in the conditional sample space, that portion of the tree. Okay, the numerator part is going to be just the part of that tree which meets the event criteria of having cancer. So it's just the top path that I've marked in red. So the probability of being there is just this one conditional, or this one and situation here, 0.05 times 0.9. So like you could say, out of these, only this path here is the one that went through cancer. So that's going to be the event. So testing positive, the bottom is the probability of all ways to test positive, and the top one is out of those ways, which ones went through cancer, 0.05 times 0.9. That turns out to be 0.24. So that's interesting. Just in and of itself, that's interesting, right? Because if you think about that, if somebody tests positive, this test is supposed to be to find cancer 90% of the time. But if you have a positive test result, there's only a 24% chance that you actually have cancer. Is that surprising? To most people, that is very surprising. And this is the reason why doctors often, if you have a bad test result, the very first thing they do is order the test result to be repeated, because the chance of having 2 false positives in a row is very unlikely, and so the probability goes up. You can work that one out. In fact, we'll work that one out as one of the examples later on when we get to the examples video. But this is the reason why doctors often repeat tests, because even with a high hit rate, if the chance of a false positive is high, then it greatly lowers the probability that we really have the disease given a positive test. Kind of surprising, but true. Okay, so we're going to define something else about these forward and backward direction probabilities. So the conditional probability going forward through the tree is different from the conditional probability going backward through the tree, which we shouldn't be surprised by that, because when we talked about conditional probabilities, we said it makes a big difference which one is the condition. Right? So going, quote, forward through the tree, that's the probability of testing positive given that you have cancer. That's 90% chance. The probability that we have cancer given that we test positive going backward through the tree, that probability is only 24%. Okay, so there are some names for these things. First of all, this backwards probability of having cancer given that we test positive, that's referred to as an a posteriori probability. Okay, this is really a probability of having cancer, but with the condition that the patient tests positive. There's another probability of having cancer. Since we're talking about probability of having cancer, if I just say what's the probability of having cancer as a simple probability without having any tests being run, that's 5%. And that's referred to as an a priori probability. Okay? Let me explain why those names are the way they are. If someone came to you from this city and they asked, what's the probability that I have this cancer? Then if you haven't run any tests, you would tell them 5%, the a priori probability, because this is the probability prior to having any further information. But if the person has the test and the test is positive, then you would give them the a posteriori probability, because if you test positive for the cancer, then there's a 24% chance that you have the cancer after having this additional information. So that's referred to as the a posteriori probability. Okay, these backwards through the tree conditional probability problems, they're sometimes referred to as Bayes formula problems, because the idea was initially described by Thomas Bayes, who was a minister, a philosopher, and also a statistician. We usually do these problems by drawing a tree and using the procedure we just followed, but to see how it relates to the formula, we could put generic events in here without any probability numbers filled in and develop the formula that's presented as Bayes formula. So if we have 2 generic events, A and B, A can happen or not happen, and B can happen or not happen, then these would be the probabilities as filled in. This would be the probability of A, the probability of A not happening, the probability of B given that A happens, the probability of B given that A doesn't happen, and this would be the probability of A times the probability of B given A, because that would be A and B happening. And this would be the same thing, A not happening times the probability of B given that A does not happen. Okay, so if we were to do our conditional probability, the total probability of the paths would be probability of A times probability of B given A, that's this path, plus the probability of A not happening times the probability of B happening given A doesn't happen. And then on the top it would be which paths went through A, which would be only the top path. So the top path over both paths, right? Now this bottom large thing, probability of A times probability of B given A plus probability of A times probability of B given A, that's all the ways to get to B, right? All the ways to get to B, and so therefore we could replace that with just the probability of B. And that formula there is the one that's referred to as Bayes' formula. You can write it this way: the probability of A given B is equal to the probability of A times the probability of B given A divided by the probability of B. So kind of a neat little formula. It just shows how you can reverse the two conditions and how they relate to each other. But I really think it's easier to solve these kind of problems using the tree diagram for the specific case that you're analyzing, instead of trying to piece together what these different conditional probabilities are in the formula. So one last thing about these a priori, backwards conditional, Bayes formula problems: the numerator and denominator can actually be made up of any number of paths. Now, to keep this video simple, I just use two paths. But there could be any number of paths. So when you see this in a textbook, it'll say something like this: let S be the sample space partitioned into n events, A1 through AN. Let E be any event of S for where the probability is not zero. The probability of any event given the event here, the conditional probability, is the sum of all the paths, and there can be many paths. And then on the top, it's all of the paths that lead through the event that you're considering. So if you're asked to use this formula, all it's saying is add up all the probability of all the paths in the denominator, and in the numerator include only the paths within the event. But you can see it's much easier to do this with a tree diagram than it is with the formula. So we'll always do problems with the tree diagram. Okay, finally, one last thing. The idea that the probability you assess that an event is true changes as you gain more information, from the a priori probability to the a posteriori probability, means that if you get even more information, your assessed probability is updated again. And that actually has some really interesting applications in a wide number of areas, including some theories of how we know things and even philosophical areas. So now that you understand how Bayes' formula works mathematically, I actually recommend watching the following video. This author here does a great job of exploring these ideas further. If you're interested in knowing the wide-ranging ramifications of Bayes' formula, you can type this in directly if you want to see this one YouTube video. Highly recommended. Okay, so that's a summary of a whole bunch of little things related to and or, conditional probabilities with formulas, and Bayes' formula. If you go to the examples, we'll look at a wide variety of problems that use these ideas.